Welcome, everyone. I'm David Bader, and I'm a distinguished professor at the New Jersey Institute of Technology, and I direct the Institute for Data Science. Welcome to this week's seminar that will be given by Manish Parashar on transforming science in the 21st century, NSF's vision for national cyber infrastructure ecosystem. Manish Parashar is currently serving as an Assistant Director for Strategic Computing at the White House's Office of Science and Technology Policy, or OSTP, where he is leading a strategic planning effort for the nation's future advanced computing ecosystem. He is also on an IPA to the U.S. National Science Foundation since February of 2018, where he is the Office Director of the Office of Advanced Cyber Infrastructure. At NSF, he oversees investments in the exploration, development, acquisition, and provisioning of state-of-the-art national cyber infrastructure resources, tools, and services, and expertise essential to the advancement and transformation of all science and engineering. He is also leading the development of NSF's strategic vision for a national cyber infrastructure ecosystem for the 21st century science and engineering that responds to the rapidly changing application and technology landscapes, as well as blueprints for NSF's key cyber infrastructure investments over the next decade. He also serves as the NSF representative for the U.S. National Strategic Computing activities led by the White House's Office of Science and Technology Policy, and served as the co-chair of the Fast Track Action Committee that developed the report titled National Strategic Computing Update, Pioneering the Future of Computing. Manish is a distinguished professor of computer science at Rutgers, the State University of New Jersey. He also is the founding director of the Rutgers Discovery Informatics Institute and the Applied Software Systems Laboratory. He is the founding chair of the IEEE Technical Consortium on High-Performance Computing. His research interests are in the broad areas of parallel and distributed computing and computational and data-enabled science and engineering. Dr. Parashar received the IEEE Computer Society's Golden Core Award in 2016, and he's a fellow of the AAAS, a fellow of the IEEE, and an ACM Distinguished Scientist. We just learned recently that Manish is going to be joining the University of Utah in 2021, where he's going to direct the Scientific Computing and Imaging Institute. So congratulations, Manish, on the new position, and we look forward to your talk.
Thank you, David. I really appreciate the invitation to present as part of this series. It is just incredible what a wonderful series you've put together and what you've been doing at NJIT and the Institute for Data Science. So in this talk, I wanted to give you an overview of what we're doing at NSF. So this talk is really wearing my NSF hat as Office Director for the Office of Advanced Cyber Infrastructure within the Directorate of Computer and Information Science and Engineering, or SISE. Before I get into the details of my talk, I wanted to give some context about what we do at the Office of Advanced Cyber Infrastructure and what exactly is cyber infrastructure. And why it is important. So at this point, I think this is obvious that science and society is being transformed by computer and data. And if you look at science and engineering in the 21st century, we have new paradigms that are being enabled by computer and data, and we're dealing with extreme scales and data-driven, compute-intensive research, right? So every field of science and engineering is transformed into data-rich and compute-intensive, right? And computational and data science are accepted as essential pillars to scientific investigation, right? So advanced cyber infrastructure really, which brings together this capability of dealing with large-scale data and compute, is really essential to all areas of science and engineering. So if you go back to the basic and ask the question, what is infrastructure, right? Because that's the basis of what we're trying to do in the Office of Advanced Cyber Infrastructure. So we know infrastructure is what we deal with every day around us, right? Whether it's our water supply, our transportation systems, our electrical grid, and so on, right? We know that it's scalable, it's robust, it works most of the time, it's secure, it's dependable, it's ubiquitous and can be shared and broadly accessible. It's mostly usable, it's performant, and most importantly, it provides value, strategic and economic advantage, and it drives innovation, right? We depend on this. No matter what we do, we depend on this infrastructure to be there, to function, and it allows us to do everything that we do. And when it doesn't work, it really causes not only individual anxiety, but also impacts business, impacts productivity, and has often quite significant impact, right? And if you go back and think about how this evolved, right, and look back over the decades or century, how these different pieces of infrastructure have evolved, we can make some observations, right? So if you look at the railroad or the electrical grid, you see that really it happens when local and national needs align, right? Funding models, they range from public and private. There's an essential interoperability and some agreements on standards so that different solutions can really work together as a whole. Often we see that there are many other factors that come in. So maybe the technologically best solution is not the one that's selected. And so there are many factors that go in. Governance is a big part of it, but requires that it operates at multiple levels and scales. And if you see, things are constantly evolving. There are new needs that are coming up. There are new technologies, but the infrastructure evolves in spite of these new needs, in spite of the technological disruptions, to continue to provide this value that it provides to society. And over the years, this has evolved into this interdependent system of systems or ecosystems that really continue to let us do what we do and to transform society, right? This has happened in the computing area as well. If you look back at the internet, right? It started not that long ago as something that was an investment that was made as a research, right? NSF had a big role in it. If you look up there on the top left of this slide, you see the first connection, the first network across 4 institutions, right, that was set up in the right. So it probably was somewhere in the 70s, right? And since then, it has evolved, right? NSF-Net was created where it said, okay, you're doing all these research aspects. Now these things have to come together and create the first network that connects these things. The goal was to provide connectivity across the large NSF computing resources. So NSF-Net was created. And then after that, NSF continued to force the different communities to really iron out technical issues and put these together so that we have a really growing and performant network that connects all these individual solutions. Moving forward, NSF helped catalyze really a commercially viable internet and got the industry to take on ownership, to build these private networks, and really focused on the future architectures and evolving technologies and research so that we're continuing to grow and create a national infrastructure that today, right, in a couple of decades now, we can depend on, that just exists most of the time and really supports a lot of innovation, not only in science and engineering, but across all aspects of society, right? And at the same time, NSF continues to invest in its evolution, right? Whether looking at new technologies, new type of connectivity, new type of instrumentations. So there's constant evolution that's happening. So if you think about computing infrastructure, NSF has always played a big role, right? So why do we need to think about cyber infrastructure? Well, if we look back at the first slide and think about where science and engineering is going towards in the 21st century, we see that the capabilities that a cyber infrastructure provides are going to be critical, right? And they're going to be essential parts to make sure that we keep on innovating, that we have the leadership in science and engineering, that we make the economic investments invest in national defense. All the aspects of NSF's mission really depends on the cyber infrastructure. And it has to be just like any other infrastructure, scalable, ubiquitous, usable, performant, and providing value. So we have to achieve in decades what other infrastructure took centuries to achieve, right? And in spite of these really unprecedented growth in the requirements of what we want to do, but also in the users, the number of users that are using this, in technological disruptions, right? So that's really what cyber infrastructure ecosystem is, and that's what we're trying to do in OAC, building the cyber infrastructure ecosystem like any other infrastructure that can really drive innovation. So with that introduction, I want to give an outline of my talk. I'll give you a quick update of what's going on at NSF broadly, and then OAC, and talk about some of the new programmatics and investments in the past year. I'll then switch a little bit and give you a glimpse into what's happening at the national stage, both in the context of the COVID-19 HPC consortium, but in the broader strategic planning activity as part of the pioneering the future advanced computing ecosystem. And then I'll talk about a few things we are looking at over the short-term horizon, and then end my talk and open it up for questions. So for those who are not familiar with NSF, really NSF champions research and education across all fields of science and engineering, right? Unlike some other agencies which are very mission focused, NSF has a very broad mandate. It came out after it was formed after the Second World War. We recently celebrated our 75th anniversary, right? There was since it was founded, but really its mission is to support all of science and engineering, and it's structured in the form of these directorates which are focused on the different areas such as biological sciences, engineering, mathematical and physical sciences, computer and information science and engineering, geosciences, but they're also cross-cutting things like the integrative activities or international science and engineering. We also have social, behavioral, and economic sciences, and of course, education and human resources, right? So these are really the key directorates, and then we have offices that serve its mission across all these different directorates. For example, OAC, even though it's housed administratively in the SISE, Computer Information Science and Engineering Directorate, its mission is across, as an office, is across all these different directorates and offices in NSF. Another way of looking at NSF is in terms of its these numbers, right? In terms of its budgets and its investments. And I'll let you digest the slide, but you can see really how impressive this is. Our budget in FY 2020 was about a little over $8.3 billion dollars, and about 94% of that was really used to fund research and education activities, right? So you can see NSF is a very lean organization where most of the money coming in goes out to the community in the form of grants and other activities. And the way we do this is through proposals that you, the community, submit. And here's just an example of what we did in FY20. 41,000 proposals evaluated, 1,800 institutions that were funded, and so on. So there are many different ways to look at this. I think the most impressive for me is the number about the number of people that are supported. 306,000 people are supported by NSF, so that's just incredible. And a lot of them are researchers and students and young faculty, right, who get their start through NSF grants, and that's just incredible. If I want to translate this to SISE, SISE's budget is it's still a current plan is in FY20 is slightly over $1 billion, right? And again, SISE spends that money to serve its community by funding research activities. A really impressive number there is, and this comes out of a study from the from the NCSES, which states that about 85% or greater than 85% of the fundamental research in computer science is really funded by NSF. And that's quite incredible, right? So that means a lot of the fundamental, federally supported fundamental research is really supported by NSF. Similarly, a very large number of graduate students are supported by NSF, right? So I think that is quite incredible. Like any other organization or agency, NSF has its priority areas which really drive its mission, its investments over the long term. Here are the 10 big ideas which were put forth by NSF's previous director, Franz Cordova. Now we have a new director, Panchanathan Sitharaman, who took over a few months back, right? But these were for the past few years, these were the big ideas that have been driving a lot of our investments and continue to drive them right now. These were the 10 big ideas, 6 research ideas, and 4 process ideas. And so they're up here. And really, these were defined as activities that were across all the directorates, right? So these were necessarily programs where program directors from all the different directorates came together to really implement that and to make awards and define solicitations, right? So this was something that was by design cross NSF. And you can see from the different areas that are part of the big ideas that it makes sense to bring all the different aspects of or different directorates in NSF to come together to address these big challenges, right? We also have something that was started a few years back called the Convergence Accelerators. And this was, I look at it as sort of the translational aspect of it, where you look at short-term implementation-oriented projects that take a lot of the conceptual ideas, work with industry to provide prototypes and solutions over a short term. And so these convergence accelerators have been going on for the past few years and are really complementing a lot of the foundational research that NSF supports and have been very, very effective. And again, if you go to the NSF site, you can find out a lot more about this. But one thing you can see, and I've mentioned this before, that cyber infrastructure really remains central to NSF's mission and priorities, right? Whether it's its core mission to promote the progress of science, to advance national health, prosperity, and welfare, or to secure national defense, cyber infrastructure is core. It's also core to its big ideas, to the convergence accelerators, or to even some of its biggest investments. For example, its large facilities, whether they are large instruments or observatories or experimental facilities, cyber infrastructure remains core, right? So, and that sort of again validates why it's an office that cuts across all of NSF, and also why we have to look at it like any other infrastructure that can really provide this core services and value to the broader science enterprise. Cyber infrastructure is also aligned with the administration priorities, with congressional priorities. For example, the National Quantum Initiative, or the American Artificial Intelligence Initiative, or Industries of the Future, right? Cyber infrastructure plays a big part of it. And just to highlight that, here is a paragraph that I took out from the recent budget research and development budget priorities memo that came out in August, right? So every year you have this, which really helps define the budget and the investments moving forward, right? I took a paragraph out here which talks about the future computing ecosystem and highlighted some words that align with what we have been doing over the years and continue to do in size at NSF size and at OAC, whether it's looking at advanced computing ecosystems, whether it's looking at fundamental R&D and test beds and experimental systems, whether it's looking at software and data solutions or public-private partnerships. A lot of these things directly align with NSF and with OAC, right? And so it continues to be central to many of the priorities that are national priorities currently, right? So for those who are not familiar with OAC, let me give you a one slide overview, right? So the NSF Office of Advanced Cyber Infrastructure, OAC, fosters a cyber infrastructure ecosystem to transform science and engineering research. And it does that by supporting production research cyber infrastructure, so infrastructure that the science community can depend on to provide them with the capabilities and capacities that they need for science, but also investing in cyber infrastructure research so that we are continuing to innovate and evolving the cyber infrastructure to adapt new technologies, disruptions, or to address new requirements that are coming down, right? And we define cyber infrastructure quite broadly. It is definitely the computing, the data, and the networking aspects, but also includes the data and software services, pilots and test beds, gateways, coordination services, aspects of public access and open science, but most importantly, the people, right? The communities, the professionals that are critical to making sure that we innovate, we operate, and we support the user community in using the cyber infrastructure. Aligned with what you saw in the budget priorities, we have been viewing cyber infrastructure as an integrated, holistic ecosystem. We realize that science happens when these different dimensions of cyber infrastructure come together, right? So that we can use the computing and the networking and the data and the software together as part of our workflow to really advance science. And so we have been looking at how we can do this and how do we create programs and work with the community to move towards cyber infrastructure that's more integrated rather than siloed. We articulated our vision in a document that was published about a couple of years back now. It's online, which really lays out this vision on what a cyber infrastructure ecosystem is and how do we achieve it. It also outlines a set of blueprints which say, okay, how are we going to implement this over the next decade? And what are our priorities in that implementation? So these are, again, online on our website. There's a URL out here, and you can find these. And just to give you an example, here are three of the blueprints that are on that website. The first one, which I'm going to talk some more about, is the computational ecosystem. But in addition to that, we also have one about coordination services, which says how do we provide the essential services so that users, the science users, can actually find and use these cyber infrastructure resources and integrate them into their science workflows and their applications. And finally, we have a blueprint out there on international networking, and this is looking at how do we connect with instruments, connect internationally, and enable science at the global level. I'm going to spend a little time talking about the first blueprint that we released, because we made a lot of progress over the last 2 years to start realizing the objectives and the plans that were outlined in this blueprint, right? So we had viewed our computational ecosystem, right, as made up of a few different components. We have the leadership class systems, which really are the large, highly specialized computing instruments that enable science that's not possible anywhere else, in any other way, right? So these are large systems that provide unique architectures, unique capabilities, and unique access modes to enable that science. Complementing that, we have capacity systems, which really aggregate and provide the capacity for the broad science community, right? And so we need to have a mix of such systems which really meet the different needs, but also provide sufficient capacity that it is sufficient to meet the growing computing needs. We've also been exploring federated resources that can leverage, for example, campus resources or cloud services, so that we can really bring these together for different reasons, just to aggregate capacity, but also be able to support workflows that need to combine different things. I need to have a data analytics engine running with my large-scale simulation so that I can do my end-to-end workflow, and how do I support that? And finally, it is so important that while we have to maintain a stable infrastructure, we have to continue to innovate. And so we have exploratory pilots and prototypes which are constantly evaluating new technologies, new architectures, new processors, and making them accessible to the science community so we can find out what role they can play to advance science and then incorporate it into the rest of our production infrastructure. Right? So I'll talk a little more about what we have done over the last 2 years to meet this vision. One thing you might have heard about is our work with the leadership class computing, which is something that we came out, I believe, in 2017 as a solicitation. And over the past few years, we've been working to implement it. We've been doing it in 2 stages. The first one, or the LCCF phase 1, was an award to TAC, the Texas Advanced Computing Center, which happened in 2018. This is one of the largest CPU-based system on a U.S. campus. It was launched as number 5 on the top 500 list for those who follow that. All right, it's been incredibly effective. Funded in 2018, it came online very quickly in 2019, and since then you can see out here the number of how effective it has been in enabling science. Right, it's been, no matter how you look at it, as whether it's a number of jobs that ran, a number of node hours that delivered, a number of users that are using it, it's just been a very effective resource. Right? And this summer, or this past spring, when we started aggregating resources and bringing them to bear towards addressing the pandemic, right, we found that a large part of Frontera could be dedicated, and it has had a tremendous impact. And I'll talk a little more about it a little later in this presentation. But more importantly, Frontera is phase 1 of our vision for a leadership class computing facility. Phase 2 is something that we have started design on, and this is going to be part of the NSF's MREFC process, right? And for those who are not familiar with that, that's the process that's used to design the large facilities that NSF funds. These are the large telescopes, the ships, the experimental facilities, the large observatories, right? So the thing here is that we look at computing as just that, a large infrastructure investment that is at par with these large shared facilities, right? And so we have now moved into the preliminary design phase of the phase 2 LCCF, and the goal is to have this large phase 2 facility be operational in the 2024 timeframe and continue to provide capabilities and capacities to the broad science community. Complementing that, we have been looking at capacity systems, both on the production side, but also in terms of innovative prototypes and test beds. And here's just a snapshot of the different investments we have made over 2 years. Again, we wanted to have the broadest set of capabilities and give access to the broader science community access to these capabilities. Right, so we have a bunch of systems, from large memory systems such as Bridges 2, container and virtualized systems such as Expanse, cloud-like systems such as Jetstream, GPU-based systems, Delta. Anvil is a more traditional campus cluster type system for applications that need that, right? And these are all integrated together as part of our Exceed ecosystem, and provide users across all of science access to this, right? So again, the idea was to create a broad set of resources for the science community to meet the diverse needs that are part of NSF's science mission. As I mentioned, innovation and balancing this stable production system with innovation is very important. So here are some of the innovative systems that we have funded. Okami at Stony Brook, which should be coming online soon in the next few months, really is the first system in the US that is leveraging the Fujitsu ARM processor that's part of the Japanese exascale project, right? So we said, okay, let's see how this architecture, this new processor with its new capabilities for high bandwidth memory access, how does it support our US applications, our science workloads? And so we'll have the system to evaluate it. And this year we funded, this summer we funded 2 AI-based systems, Neocortex at PSC, which is looking at the Cerebrus wafer scale AI processor, and Voyager, which is looking at really neomorphic solutions, right? Again, these systems will come online sometime, I would say, next year or late next year. And again, they'll provide these capabilities to the science community to see how effectively they serve our science needs. And if they turn out that they're very useful, then they get incorporated into capacity systems and become part of our infrastructure. And so that's where we are continuing to innovate while maintaining stability. And I think that's very, very important in any infrastructure, and especially in cyber infrastructure. Just to round this up, we recently funded a project called PATH. And what PATH does is it builds on the technologies behind HT Condor and OSG, and provides a federated resource that allows me to run high throughput jobs across this federation, right? So we have investments at these large resources you just saw on the previous slide, but also at the campus level and in the commercial cloud. How do we use them collectively to enable science? And so PATH provides this fabric to connect all these different investments to provide this capacity for these high throughput jobs. And this comes from a realization that the requirements or need for computing is only going to grow, and we need to leverage all investments in all computing and bring them to bear towards enabling science. And HT Condor gives us one mechanism to do that. So I could really, the idea behind here is to be able to submit locally and then run across this entire federation, whether you run on resources on one of these big centers or on campus resources or on the cloud. You could do this through this one way or one interface. And so that's very, very powerful. And of course, clouds have to be a big part of it. And we have been trying to explore how can we integrate clouds as part of our infrastructure, of our ecosystem. For example, as part of Cloud Access and the Cloud Bank project, we are finding we are funding ways, or we have implemented a mechanism where you can, as part of your grant of your proposal, request cloud resources, right? And then if it's awarded, you can access those cloud resources. So what happens is NSF provides resources to Cloud Bank so that you can get access to resources in the cloud of your choice, right? And this sort of allows you to really use the entire funding to be able to get access to these cloud resources without having to pay overheads and things like that, right? So it's a great way to be able to access it. It's still a pilot, so not all programs have bought into it, but a lot of our size programs really allow you to do that. A big question comes up is, can our traditional science applications use the cloud? And so we funded a pilot with Internet 2, where we can allow you where we are really investigating how production science workflows can run on the cloud. Are there any fundamental barriers? And this has been extremely successful in what they've been able to do. But more interestingly, we are seeing how can the unique capabilities that clouds provide, for example, elasticity, for example, special purpose accelerators like TPUs, right? How can they be used effectively to advance science, right? So the lessons learned there are quite incredible. And again, you can go to the ECAS site and Internet 2 and learn more about what the outcomes of this study is. And finally, we are working with campuses through the CC Star program and other programs to be able to integrate cloud services into capabilities that are present at the campus level. Again, the idea here is to not use clouds instead of, but to build an ecosystem where we can use clouds where clouds are most effective, and using other infrastructure, other computing capabilities where they are more effective, so that they can be combined. So it's really traditional computing and cloud, and how do we use them in an integrated cyber infrastructure ecosystem. Switching a little bit, I wanted to give you a few more updates. One thing I wanted to highlight was the intersection between cyber infrastructure and artificial intelligence. Clearly, there's an increasing importance of investments in cyber infrastructure, in artificial intelligence, and there is a good overlap between the two. And we have been exploring this most recently. We had a workshop last February, and there's a URL at the bottom there, smartci2020.org, that explored this intersection. For example, cyber infrastructure can provide the capabilities to run your AI, right? Whether you want to do learning on a large data set or do real-time inferencing, how do I create how do you create the cyber infrastructure capabilities to support this? We're also looking at increasing workflows that combine AI with science, right? So I'm doing online data analytics. I'm maybe doing actuation online using AI techniques. And how do I combine those capabilities to be able to do deep learning along with my more traditional modeling and simulation as part of the workflow? People are also looking at how can I do science which is driven by through data using AI. Can I use AI to build models, and what can I say about those models? And we've been supporting both the research and the infrastructure to support that. And also, and complementing all of this, we are looking at how AI can help us build a better infrastructure, better cyber infrastructure that's more robust, that's more secure, more agile, more performant, more resilient. How do I use cyber infrastructure in the fundamental design of CI and its services to improve the CI itself, right? So if you look at the most recent AI Institute solicitation and you look at theme three, you can see that a lot of these things are part of that, and we're looking forward to the community responding to that in their proposals. I think this intersection is incredibly important, and we're looking forward to getting a good set of proposals here. Switching a little bit, and I should wrap up soon. A few things on the national stage. COVID-19 HPC Consortium. I'm not sure if you're aware of this, but back in March, when we were seeing the role that computing, cyber infrastructure is going to play towards understanding the virus, building treatments, regimens, just being able to come up with a way of addressing and fighting this virus, we got together a bunch of, under OSTP's leadership, industry, academia, agencies got together and said, how do we bring all our capabilities, all our capacities together and make them accessible to the science community as they try to address this pandemic, right? So, and it's just incredible how this came together, right? It really happened in a matter of weeks, right? The actual portal was put together by the Exceed team in really a weekend, right? Everybody stepped up. Industry said, sure, we are part of it. Google, Microsoft, IBM was in a leadership role, and so on. Everybody, Amazon, everybody started Hero Resources. All the computing centers stepped up and said, we'll be happy to provide resources out here, right? So within weeks, we were able to set this up, get applications running, get computing in the hands of researchers that needed to use it, and more importantly, get expertise to the researchers so they could use this computing resources, right? We started off, and within a few months, we were up to 73 members. In fact, a bunch of different countries really joined because they saw what an impact we were having. For example, the UK, Switzerland, Sweden, Japan, South Korea, Australia, right? A bunch of countries are part of this consortium at this time. Aggregate, we have about 600 petaflops. That's growing. That number is already outdated. We have serviced more than 90 projects. Some are completing. And an interesting thing from an NSF perspective, right? Just because of the nature of our mission and our priority to create resources and a computational ecosystem that can be broadly used across science, right? It is the most sought after resource as part of this consortium, right? A large fraction of a large percentage of the projects are running on NSF resources, right? And that's just a testament to the effectiveness and the ability of these resources to serve a really broad set of science needs. On the left of this slide, you see two results. The one on top is interesting. This is done by one of OAC's career awardees, Amanda Randall from Duke University, right? And what she was doing was to understand the airflow within a ventilator to see how we could split it across multiple patients, right? And when this was a critical resource, this was just incredibly important to do, right? So she said, look, I need to do this. She came in, she paired up in Microsoft. Over a weekend, they ran all their simulations on Azure. And within that weekend, they were then able to take that to FDA to get early approval, right? So it just accelerated that tremendously. On the bottom, you see research being done by Romy Amaro on Frontera. She's at UCSD, and this is one of the the highest resolution simulation of the virus spike atomic structure, and as well as its atomic dynamics. And it's just the understanding you get by having this at this resolution is just incredible. Again, you can go to the websites and get more information about these, but this is just a snapshot of what this consortium is able to do, and also highlights the importance of having such a computational or cyber infrastructure ecosystem that you can bring to bear not only to this pandemic, but you can think about bringing it to any national crisis, whether it is a hurricane or forest fires, where you need to have modeling and simulation and data analytics to work together. You can think about how you can aggregate. And if you have the cyber infrastructure, you can do this very, very effectively. Another aspect of our response was Rapids. And this was these quick grants that we give. And these, again, had huge impact. I'm not going to go through all of them. I'll just highlight one. For example, the project from West Florida and Ashok Srinivasan that's getting a lot of press. What he did was studied how using data coming from different edge resources, for example, cameras, how do we understand how effective social distance is? How do we take pedestrian dynamics into understanding the social distancing, and then use that to adapt policies so that they're more effective, right? For example, he studied how the virus would spread in an airplane, and then how can you address that? And that has been getting a lot of press. So this is just incredible impact that we've been able to have by providing resources and funding to researchers in a timely manner to the RAPIDS process. Switching gears once more, I wanted to give you a quick update before I start winding up. So some of you, many of you are aware of the NSCI that was launched in 2015, which really set up many of the national priorities in computing, including the exascale program in DOE, right? There was a general view that, since 2015, technology has evolved, as have the science needs and the science, the application priorities. And so it was time to rethink the objectives of the original NSCI. And so OSTP put together a fast track action committee that worked with the community to start thinking about what the priorities should be moving forward. How should these objectives be updated? We worked with the community. I co-chaired the FTAC to really address and find out what are the priorities moving forward. We had an RFI. We had a community of interest meeting. David was kind enough to participate and give his inputs. As part of that, we had a bunch of different community events, and we really came up with a set of objectives as part of an FTAC report in November 2019. And at a high level, what it said was that we really need to think of computing as an ecosystem that can collectively be brought to bear to address the challenges of the day, that software and data are very important parts of this ecosystem, and sustainability of software and data is very, very important. And finally, making sure that we have the expertise, right? The workforce that can be part of this was very, very important, right? So these were sort of the high-level themes that came out of the FTAC. Over the summer, during my time at OSTP, I've been trying to put this into action. We set up a NSTC, National Science and Technology Council subcommittee that's focused on the future advanced computing ecosystem. We put together a community convening to start looking at what the strategic objectives should be over the long term. And then we are working on building a whole of nation strategic plan that can then be used to implement these strategic objectives and really define investments, priorities over the next decade. And here are some of the issues that came, or some of the objectives that came out of our meeting that we held, the convening that we held in August, right? I think, again, I'm not going to read through that, but the bullets, I think, are the most important here. First thing was to realize advanced computing ecosystem as a national strategic resource collectively, right? It's not an individual, but when you put all these pieces together, the high-end systems, the cloud resources, the campus resources, the capacity resources, put them, test beds, put them all together, right? That's the national resource that can collectively advance science. And that's really driven by the science needs that we see down the line, but also the rate of innovation that we are seeing in technology and in computing. Make sure that we have a innovative and trusted, usable, sustainable software and data ecosystem. Make sure that we have foundational research that's looking at emerging technologies, emerging needs, but also make sure that you have the translational aspects so that those innovations can be brought to bear towards advancing science. And as I mentioned before, making sure that we have a capable workforce, right? So these were the pillars of this strategic plan that's being developed, right? And these came out of this convening, and that in the community discussed them and brought these. And of course, partnerships between government, academia, nonprofits, and industry are an really integral part of this vision moving forward. I will go through this quickly, just a few things we are interested in looking forward. We've been working on implementing this blueprint, and I'll say just stay tuned and on what this the implementation is look like, what the programmatics around this is going to look like. One thing that we are spending a lot of time is workforce. As you must have realized, it came up in all the discussions I've talked about so far. It is one of the critical things for us moving forward, and so we have been working a lot on defining how do we support this workforce, especially in the center of this slide, not only the contributors and users, but the CI professionals. These are the data experts, the CI experts, the software experts that are critical to many of the projects and to the smooth operation of the CI infrastructure. How do you make sure that they have the career paths, the reward structures, the stability that they need to be able to, to be able to meet the needs of this community. We had a workshop in September last month that really focused in on how do we do this as a community, and we have been the report should be out soon, and we are looking forward to then translating those into programmatics, both at NSF, but collectively across the agencies to be able to move this and address this problem, right? I think this is one of the highest priorities for us at OAC, and we'll be spending a lot of time on this. Security is of growing importance, and I think we have to define security, cybersecurity more broadly. It's definitely the more traditional, but I think it goes on to include things such as trust and provenance and integrity, and spans all aspects of it, whether it's ensuring reproducibility, whether it's enabling collaboration, production science. And this is not something, as you all know, that we can just layer on top of solutions. So it has to be built into the foundational aspects of what we do at OAC. And so we are looking at how do we integrate these different dimensions of security into our programs, right from the core, our software, all our programs, so that we start addressing these needs of security, of reproducibility, of collaboration, of privacy, of trust, right into the basic building blocks of a cyber infrastructure ecosystem. Missing middle, some of you have heard me talk about this before. I think this is coming from the realization that we have invested a lot at the endpoints in creating the capabilities, but often when you try to bring them to bear collectively towards enabling science, we find that there are gaps, right? How do I combine different data sources along with computation, along with expertise, along with analytics to be able to do the science that I need to do, right? And this goes back to our vision of an ecosystem, right? So we're realizing that we have a lot of the pieces, but we need to focus on connecting them together, especially in an era of large data, streaming data sets, where being able to transform those data streams collectively towards insights and discoveries is very important, right? So addressing this missing middle is another priority for us moving forward. And finally, and I think this might be my last slide, one thing I've come to realize is that we do address the different pieces of this arc, right? We do address a lot of research. We address prototypes and community framework, and we build sustainable services, right? But we do them separately. If we want to translate a lot of our research into sustainable services, many times that pathway to production doesn't exist. And researchers who want to do that have to struggle to make it happen, right? And since there's so much innovation going on that can really impact science, we need to provide these pathways. We need to support this translational arc so that we can take innovations in CI and give that innovation a pathway to move to community solutions and possibly to sustain services that can support the entire community, right? And so we've been thinking about how do we support that arc? How do we enable the translation that's needed to allow our innovations to really impact science in a more deliberate, in a more structured, and in a more timely way, right? So that's something we've been thinking about, and how do we develop the programmatics around it to support translation. I'm going to skip this. We're doing a lot of strategic thinking in data and software. You've seen some of these reports that are on the right side of the slide. All I'll say is stay tuned. This is another part of something that we have done a lot of thinking on and we're ready to act on. So we'll build the blueprint and then we'll start building programmatics around it. I think that was really my last slide. I'm going to pause, leave this on while I open it up to questions. This lists a set of opportunities that are relevant and are open right now, right? These have deadlines coming in. Some of them are today, like CSSI, I believe, has a deadline today. So I don't know how useful that will be, but I think some of the others have deadlines in the future. So again, you can go, and the easiest way to find this is take the number NSF-21 or 20-something, put it into Google, and they'll take you right to the solicitation. I'll stop here and hand it back to David, and I'll be happy to take any questions. Thank you.
So thank you. And if anyone on Zoom would like to ask questions, please put them in the chat. Thank you to all of our audience on Zoom and also on our YouTube stream. And Manish, thank you as well for such a wonderful talk and such a comprehensive talk. It's really great to see all of the work you're doing, and we really appreciate all of your dedicated service both to the nation and the national science community. So thank you so much. Maybe I can start with the first question and just ask you, now that we see data as the fourth pillar of science, how do you see data being integrated with the cyber infrastructure going forward as we go through these new visions? Where do you see data playing a role?
So I think data really cuts across every aspect, right? And it has many dimensions. You have the collection of data, so you need the ability to connect instruments and provide them with the capabilities to collect that data and to bring it to places where it can be processed. But more importantly, when that's not possible, you need to be able to have resources that are close to the data that can be leveraged. For example, we have funded a bunch of projects such as the PRP, the Pacific Research Platform, which is looking at data transport nodes that are beefed up to be able to process data close to where data has been acquired. We have the SAGE project, which is a mid-scale research infrastructure project, which is looking at how do we integrate these different pieces in a programmable way so we can have data-driven applications that connect for the data instrumentation, the data collection with the processing as part of this, right? We have computational platforms that are really designed for data-intensive science. Bridges is this large high memory capacity systems, right? That support large-scale data analytics. We've been working with cloud providers to provide those capabilities. And then finally, we've been funding data services, data infrastructure, both exploration elements, research, to be able to build the next generation data cyber infrastructure that can continue to support science. So really, it has to cut across every aspect of the cyber infrastructure, and we have a bunch of programs that support that.
Thank you. And maybe another question. You have such an interesting vantage point looking at the national science strategy while serving the Office of Science and Technology Policy in the White House. I know that we're in an election year. How do these big projects like our cyber infrastructure be sustained through multiple administrations potentially of the federal government?
So, I mean, this again, it's the history of NSF, right? These science investments continue because science really cuts across everything, right? In a sense, it is cross-cutting, and the science priorities cut across. And again, NSF has its budget, is defined across across the, as you've seen in its 70+ year history, right? It's sort of cut across administrations and different political leanings, because again, the scientific investments really cuts across a lot of that. I know I'm not directly answering your question, but yeah.
So I just wanted to thank you again for a great talk, and thanks to all of our audience. We have a talk coming up every Wednesday at 4 p.m. Eastern. So thank you again, Manish.
Thank you, David. Thank you for inviting me, and I appreciate everybody's attention.